So hello, welcome everyone. We were in 8-20. That is for the DA converter, we had V reference equal to 2 volts, R reference equal to 500 ohms, RF equal to 1.5 kilo ohm. We need to calculate the output voltage when the input is D7, D5, D3, D0 is equal to 1, and D6, D4, D2, D1 is equal to 0. So here the binary number will just corresponds to 10101001, okay, and that will be 169 decimal equivalent. So there are two ways of handling this. You can find the step size and multiply with that 169 value, or you can directly substitute in the formula which is given over here, right, which is given over here. So in this formula you can see that it is V reference by R reference into RF, D7 by 2, D6 by 4, D5 by 8, D4 by 16, D3 by 32, D2 by 64, D1 by 128, D0 by 256, right? This is the formula which is there. You can just substitute. Otherwise, the step size will be V reference, this same, that is V reference by R reference into R reference divided by 2 to the power of 8. 2 to the power of n is 8 here, okay, that is 2 to the power of 8 is 256, okay. So to this you divide it by 256, then you will get the value of the what you call step size. That step size you multiply with the binary value which is converted into the decimal, that is 169, you will get the value of the output voltage. In both the cases, you should get the same value. You can try both the ways. Okay, you'll definitely find that both are just the same because we are just taking 256 common from the denominator here, which is 2 to the power of 8, and rest of the thing will be the decimal equivalent of the binary number. Okay, decimal equivalent of the binary number. Fine. So having finished this, so we are trying to see this 8.24 for the small signal half wave rectifier of the type. Draw the output waveform if Vin is 300 millivolts peak sine wave. So for this is the figure, positive small signal half wave rectifier circuit, and in this we have here peak value 100 millivolts, but what is given in the problem is 300 millivolts peak. So try to differentiate between peak to peak and peak. Now in place of this 300 millivolts we'll have 300. In place of this 100 millivolts we'll have minus 300. Okay, so we'll get half wave like this. Okay, positive half wave. Diode is on here in the positive portion, off in the negative portion. Now if you reverse it, if the diode is reversed, then the diode will be on during the negative portion and off during the positive portion. That's all. So the next one is that only. Repeat the problem 8.24 with the diode reversed. So if the diode is reversed, what happens? Then you will get only the negative half, and that is, I think, given directly here. So same thing is here. Okay, so you will get this. So now this will be again plus 300 minus 300. This will be minus 300 millivolts, and we'll have the half sine wave with the diode being reversed compared to the earlier case. Okay. Next, we will go for the filters. Okay, the filters. So here we have the cutoff frequency of a certain first order low pass filter is 2 kilohertz. Convert this low pass filter to have a cutoff frequency of 3 kilohertz by using the frequency scaling technique. Okay, so before taking this problem, let us try to so to say see a example of whatever is given in the book. Okay, even we can see the procedure of doing that, and then we can see the example either way. Okay, so here we are given the steps. Okay, filter design. A low pass filter can be designed by implementing the following steps. Choose a value of the high frequency FH. Select a value of C less than or equal to 1 microfarad. Generally use mylar or tantalum capacitors, which are recommended for better performance. Then find the value of R by using R is equal to 1 by 2 pi FHC. We know FH and we know C. We have chosen the FH and we have chosen C. Okay, so then you can find the value of R, and that value will not be the exact value which is available. C will, you can choose whatever is available from the appendix, standard values, right? C can be standard value, FH can be any value chosen. R will not be a standard value, therefore you need to use the so to say potentiometer a little above whatever we have got, so that we can move the potentiometer in such a way that we fix the value which is that much. Then AF can be found by using the formula 1 plus RF by R1. Then we have frequency scaling. Frequency scaling is a process wherein we can see that here, right? We have designed for one frequency, but we want it for some other frequency, FH dash. We have designed for FH and we want the filter for FH dash, then we can apply frequency scaling. So in this case, either the R or C, not both, either the R or C, not both, okay, should be, multiplied by the ratio of the original cutoff frequency to the new cutoff frequency. That is, to either R or C, you multiply FH by FH dash. Then you will get the what you call filter, okay, filter with that resistance for the frequency FH dash, FH by FH dash into R or either R or C. Okay, you can multiply not both of them to get the new filter, right? So that's what is done over here also. He has done that only. Design taken FH equal to 1 kilohertz, C is equal to 0.01 microfarad. R, he has tried to find 15.9 kilo ohms by writing 1 by 2 pi FHC. Because this is not available, standard value of this is not available, right? 15.9 kilo ohm is not available. You can see in the appendix, right? What is available is 18. 18 is available, 16 is available. Okay, nearest value 16 is always available. You can choose that, or you can use the plot and vary it properly so that we will get that value. So he has chosen a part. You can choose even the 16 value also, which is approximately same as 15.9. You can always say that. Otherwise, a part will be a better solution. Having done that, then AF is equal to 1 plus RF by R1. So in this problem, he has told the passband gain as 2. So 2 is equal to 1 plus RF by R1 will give RF by R1 is equal to 1. So RF will be equal to R1. So therefore, we can just choose the value of R1 equal to RF equal to 10 kilo ohm. Okay, RF is equal to R1 is equal to 10 kilo ohm. Then in the frequency scaling technique, the original value was 1 kilohertz. We want to design for 1.6 kilohertz. So the ratio of that turns out to be 0.625, and that value is to be multiplied with the value of the R. Okay, the value of R. And that is 15.9 9 kilo ohm into 0.625 is equal to 9.94 kilo ohm. And again, 9.94 kilo ohm is not available, so standard value 10 can be chosen, or you can choose a potentiometer of 10 kilo ohms and vary it such that you get a value of 9.94 kilo ohms. Okay, you can use a potentiometer of 10 kilo ohms and vary it such that you will get 9.94. You can as well use potentiometer of 20 kilo ohm also and vary the potentiometer such that you get 9.94 kilo ohms. And that will give us, if you substitute over here, the FH value will turn out to be 1.6 kilo ohms. So going back to our problem over here, right? We design it for 2 kilohertz and use the frequency scaling technique to find for 3 kilohertz. Okay. So for this, what you need to do again, follow the same procedure, right? FH is equal to 2 kilohertz. C, you can again choose the same value if you want, right? Or you can use the value of 0.047 microfarad or a little lesser than this, whatever you want, right? The values are, again, it should be from the standard value, capacitance standard value, okay? So standard value is here, you can see that, capacitance standard values. So he has chosen 0.01. So one should remember when we choose the multiple, what you call standard values, that will just give you the multiple values of this, right? So for R, you can choose the value over there, whatever is available, okay? So 0.001 multiplied by 10. 10's multiples will always be available. 0.01 microfarad. 0.01 microfarad is what you might choose. Okay. So that is what he has taken here also. 0.01 microfarad. So if you want, you can choose some other thing also. But accordingly, the value of R will change. So FH is equal to 2 kilohertz. C is equal to again 0.01 microfarad. R will be definitely 1 by 2 by 2 kilohertz, that is 2 into 10 to the power of 3 into 10 to the power of minus 8. And that will definitely give double of this value. Okay. Will it be double? No, it will be half of this value. So that will give us 7.95 kilo ohms. Okay, 7.95 kilo ohms. Again, that is not available to us. So therefore, you can use a 10 kilo ohm part and then vary it such that you'll get 7.95 kilo ohms. Okay, the RF R1 values are not asked here. So if you use passband gain of 2, then definitely you'll get R1 equal to RF. You can choose the value 10 kilo ohm. But the problem given is second part is also there, which is the 3 kilohertz. So you need to take the original value FH, which is 2 kilohertz, divided by FH dash, which is 3 kilohertz, 2 by 3 into 7.95. That will give us the value, which is 6.5 kilo ohms. C value will remain same. C value will remain same, whatever we have chosen, but the R value will vary for that and we'll get 6.5. Again, you can use the 10 kilo ohm part and just vary the thing to get the 6.5 kilo ohm. Now, just see in the appendix directly whether the resistor of 6.5 kilo ohm is available at all. No, 6.8 is available, 6.5 is not available. Okay, so might be it is better to use the part, but even for that matter, 62 is available and 68 is available. Right, 62 and 68 are available. So correspondingly, you'll get that 6.2 or 6.8. So therefore, you can divide by 1000 and all that and multiply by 1000 and all that to get the standard values. Okay. So we'll get there the potential value there. Okay. Now we'll go for the next problem. Draw the frequency response curve for the low pass filter in the problem 7.1. So for that, we again go over here how he has drawn the, plot. For that, you need to use this equation. V naught by V in is equal to AF by root of 1 plus F by FH whole square. Okay, AF divided by root of 1 plus F by FH whole square. So for this, for different value, FH is, common, that is 6.65 kilohertz. So for that value, right, and for different values of F, which are much below 6.65 kilo ohms and much above till, from much below values of 6.65 kilo ohms, 6.5 kilo ohms and much above the 6.5 kilo ohms, we should be able to find. So just keep that in the, what you call FH should be the central value for F. So that means if you see here, we had taken, in this problem, the, problem 1 kilohertz is the value over here. For 1 kilohertz, we use plotting, right? So 1 kilohertz is kept in between. Below values, he has taken some. Above values, he has taken some, right? Similarly, we should do that there also, okay? So at the, FH value itself, you will have 1.41 times. 1 point, rather it is, 0.707 times root 2, 1 by root 2 times divided by root 2. Okay, this will be equal to, if F is equal to FH, this will be equal to AF by root 2. AF by root 2. So for all different values, you can choose the same values also if you want. Okay, 10, 100 to 200, 700 and all that. Or might be you can use 10, 50, 100, 500. Is that those values are better? 10, 50, 100, 500, 1000, 5000. Then after 5000, you better choose the value of 6500 because that is the value needed. Then you can go for, 10,000, 50,000, 1 lakh, 50, 5 lakhs, and so on. That might be more better. Okay, whatever it is, then so that you can, plot it on the scale, right? Of the, you can use a log scale or whatever you want, right? Yes, put here a scale. This is the log scale here for F. 10, 100, 1K, 10K, 100K. This is log, whereas this will be normal, values. Okay, y-axis normal values in dB, 0, minus 10, minus 20, and minus 30, right? Here it will be the values which is, in the log. So what he has tried to do is, here you can see that, he has taken this and then tried to find the dB value. dB value is 20 log of this value. That is what is to be plotted, 20 log of this value. So that x-axis is also the logarithm of the logarithmic plot, and y-axis is the logarithm of the gain magnitude, which will turn out to be this. Then you can plot it. Find this and plot that, right? That is what you need to do. Next, obtain the frequency response data similar to table 7.1 for the first order low pass filter with cutoff frequency 2 kilohertz and a passband gain of 1. Construct the frequency response plot from this data. So now only thing changed is the, what you call, low pass filter. Okay, low pass filter, we need to, what you call, get it with 2 kilohertz. Okay, with a 2 kilohertz. Pass band gain of 1. Pass band gain of 1 means AF is equal to 1 plus RF by R1 is equal to 1. And that will give us the value of RF by R1 is equal to 0. And that will give RF equal to 0. And that will give us only that the amplifier which we have connected is a voltage follower. Okay, only case is voltage follower. Okay, so RF will be equal to 0. R1 you can choose or you need not choose because it just is a voltage follower. Okay, so you can just have to mention that, and then the frequency response can be found out for the same. That means AF will be equal to 1, and this is 2 kilohertz only. And for this 2 kilohertz value, which is mid frequency, above and below that, you just take those values and try to put it in the table, and then find out the for each of those frequencies the V naught by Vn, and then take the logarithm 20 logarithm of V log by Vn, and then both that the x-axis frequency versus the dB value we can try to plot. Okay, we can try to plot, but that you have to plot it in the logarithmic scale. Okay, logarithmic scale. Fine. So if you want to be very accurate, then you can have your logarithm graph sheet and then draw it and upload, or otherwise if you write a logarithmic plot as it is written over here, that is sufficient. Okay, you can mark equal divisions from 10 to 100, 100 to 1k, 1k to 10k, and 10k to 1000. Okay, so that is the way we can find out the what you call design. Now let us go to the next one. Obtain the frequency response data similar to the table 7.3 for the first order high pass filter at a cutoff frequency of 400 hertz. Oh, sorry, this is obtain frequency response data similar to for the second order low pass filter at cutoff frequency 2 kilohertz. It's not first order, I am wrong. So I made a mistake, right? It is second order low pass filter. So for second order low pass filter, this is the case we need to consider. So second order low pass filter is something like this. We are trying to solve 7.4. We have made a mistake earlier. Now 7.4 is corresponding to second order, which looks something like this, right? Here we have two set of RCs, right? R1 C1 and R2 C2. You can put it whatever you want, or R2 C2 and R3 C3 he has put because he has used R1 over here. We can say R2 equal to R3 equal to R, and C2 equal to C3 equal to C. You can consider that. And here you have RF and R1 and the values of the what you call this corresponds to a so to say this corresponds to a so to say non-inverting amplifier, because input is connected to plus. Okay, input is so non-inverting amplifier, which is having the RC network, will become the second order low pass Butterworth filter. Now when we talk about this, right, when we talk about this, then filter design is choose the value of the higher cutoff frequency fh, choose R2 equal to R3 equal to R, and C2 equal to C3 equal to C, and we choose the value of C, which is less than 1 microfarad, which might be again 0.01 microfarad you can choose, or 0.047 or 0.0047 microfarad you can choose. Okay, whichever you want. Again, for that you need to go to the table of the appendix for the capacitance, and then from these values you can choose whatever you have, right? Having chosen the value corresponding to that, and then we can choose the 2 kilohertz frequency there. So R will be equal to 1 by 2 pi 2 kilohertz frequency, with the value of C chosen there might be, which is 0.01 microfarad. Whatever you get over there, approximately, you can choose nearest, or you can use the potentiometer in place of that, and complete it. Then for the passband gain, now passband gain for the second order Butterworth filter is compulsorily 1.586. Only for this it is going to work. So for that, RF will be equal to 0.586 R1. So if you choose R1 equal to 10K, then RF will be equal to 5.86 kilo ohms. So for RF, you need to use the potentiometer of 10 kilo ohms and vary it in such a way so that you'll get 5.86 kilo kilo ohms if you choose R1 equal to 10 kilo ohms, right? So R1 should be chosen somewhere which is less than 100 kilo ohms. We have used 10 kilo ohms, and you can calculate the value of RF. So this is the process which we should consider. He has taken for 1 kilohertz, C2, C3, he has chosen 0.0047. For that, he is getting R2, R3, 1 by 2 pi FH multiplied by C, which is same thing as C2, C3, and we'll get 33.86. We can use the value which is 33 kilo ohms, or you can use a 50 kilo ohm part and then vary it such that we can get that 33.86. Approximate values can also be used. Okay, find RF, which corresponds to whatever he has chosen 27 kilo ohm. For that, he is getting 15.82 kilo ohm. This is not available, therefore he is using a 20 kilo ohm part. All the values he is putting over here. R2, R3 is 33 kilo, C2, C3 is 0.0047 micro, R1 27 kilo, RF he has found it to be 15.8, which is solved by writing a 20 kilo ohm part. So you need to do the same, only that here it is 2 kilohertz. So if you substitute 2 kilohertz here, you might get half of all that. So in place of 33.86, you might get 16 point some value. Okay, 16 point some value. So you can choose 16 kilo ohms for that, and then again you can use the 27 only, or might be 10 kilo ohm, and find out the value of RF. If you use 10 kilo ohm, that will become 5.86. Use the 10 kilo ohm part to solve that problem. Okay, this will become 16.9 whatever. Okay, 16.93. So out of that you can choose 16. Even you can choose 18, whatever you want, right? Or you can use a part of 20 kilohertz, and what you call, move it in such a way that it becomes 16.93, right? So in place of the figure over here, these two also might become parts. Okay, possibilities, these two also might become parts. Okay, so that doesn't matter. Only the cost is going to increase if you use the part. So next is obtain the frequency response. Okay, data similar to set for the first ordered high pass filter at a cutoff frequency 400 hertz and a pass band gain of 1. So if we go for high frequency filter design, first ordered high pass Butterworth filter, you need to exchange the positions of R and C. If you have capacitor here, it will be low pass, which is integrator. If you have resistor here, it will be high pass, which is the differentiator. Okay, high pass or differentiator. So for that, we will get the V naught by Vf is equal to this formula, right? Then AF is equal to again 1 plus RF by R1. You need to remember this, right? So V naught either this or that. So these two, this one and this, okay? So using these formulas, you can just try to find out. You might have given an example, right? So he has taken that V naught by Vin. Design a high pass filter with cutoff frequency 1 kilohertz, pass band gain of 2. Plot the frequency response for part A. So FL is equal to, FH is equal to FL. Let us choose 1 kilohertz and C equal to 0.05 microfarad. R will be equal to 15.